Hello all, as a continuation of my lecture series in the subject special electrical machines. So we have already discussed about the construction, operation, working principle along with EMF and torque equations and also the controller part. And now we are going to derive the equation for torque. So torque equation of PMSM is the topic which we are going to discuss now. So similarly, before going into the torque, we have to analyze how about the ampere conductor distribution and flux density distribution. So here we have two waveforms. One is A, which is ampere conductor distribution. Another one is B max, which is flux density distribution. So here the total angle for one half cycle is pi by P, where we have taken the half of the angle. So the starting there will be some difference, so which is mentioned as pi by 2 minus alpha. So this is how we are going to choose the angle with respect to ampere conductor and the flux density distribution. So here we all know that the flux density equation is B is equal to B max sin P theta. So along with that we have an angle difference, that is pi by 2 minus alpha. So we are going to add the pi by 2 minus alpha. So from this B is equal to B max sin P theta plus pi by 2 minus alpha, which is the angle difference in the distribution waveform. So B max sin, in order to reduce the equation, in order to use the formulas, here we are going to, in order to reduce the formulas, here we are going to replace the value, that is P theta is kept inside and pi by 2 is brought it outside. So this becomes sin pi by 2 plus P theta minus alpha. So here we can write it as sin A plus B, which will give you B max cos P theta minus alpha. So sin A plus B sin pi by 2, sin pi plus theta. So sin pi plus theta is cos theta, so cos P theta minus alpha. Similarly, equation for ampere conductor density, which will give you A is equal to A max sin P theta, and from the with this so torque is developed with the force. So the equation for force experienced by the armature conductors can be written as B L A into d theta, where B is flux density and A is ampere conductors. So by substituting the equation for B and A, which we have in the above equation, is substituted in DF equation. So that becomes A max B max L sin P theta and cos P theta minus alpha with respect to d theta. Coming to dt equation, so d force dF into radius. dF into radius will give you dt. So the A max B max R into L sin P theta cos P theta minus alpha into d theta, the same equation which is multiplied by R. So dF is equal to dt into dt is equal to dF into R. Okay, so the torque experienced by the armature conductor per pole. So in order to calculate per pole, we have to integrate. So with the limit 0 to pi by P, which is for first half cycle, so integrate the dt equation. So we have dt equation as A max B max RL sin P theta cos P theta minus alpha into d theta. So by integrating, so we have substituted the dt value. So A max B max R and L will be constant, so that is brought outside. So sin A cos B, the formula will be 1 by 2 sin A plus B sin A minus B. So with that we have got that above equation. So by integrating sin 2 P theta minus alpha, we get cos 2 P theta minus alpha by 2P. So minus so integrating sin will give you minus cos. So minus cos 2 P theta minus alpha by 2P plus with integrating with respect to theta will give you theta sin alpha. So by substituting upper limit and lower limit, we get the equation A max B max RL by 2 pi by P sin alpha. So for this, let us consider for two poles. So the above equation is multiplied by 2P. So the final torque equation is expressed in terms of pi A max B max RL sin alpha. So this will be the final torque equation of permanent magnet synchronous machine. So where if it is beta, that is torque angle, or power angle. If we substitute alpha by beta, we have to substitute minus alpha, and that beta is called as torque angle or power angle. So in this video we have discussed about the torque equation with respect to ampere conductor density and flux density. So with which of the following statement is false in the context of the characteristics if synchronous motor? So which one is false is they have a constant speed operation, or they have a low operation efficiency, or synchronous motor have high power factor operation, and they are made in large in sizes. So the option is 1, they have low operation efficiency. Coming to which of the following statements are incorrect? So of the synchronous motor has a starting torque, speed varies from no load to full load, or it can operate at lagging, leading and unity power factor. So I guess the answer is both 1 and 2. It will have a starting torque and the speed varies from no load to full load. Thank you.